My name is Alex Bedig. I'm a co-founder, current head of product, and original developer of the Opti company and platform of technology. Opti is a collection of engineers and business professionals who are working to provide connected products to the stormwater management districts, municipalities, cities, and private entities that are regulated by them. Our products are the result of research that began in 2006 and continue to innovate on the frontier of providing solutions that enable the management of many units of stormwater infrastructure to achieve larger goals for our customers. Our customers use the IoT-enabled technology that we provide to get better visibility into the performance of their stormwater assets of all types across their portfolio and to enhance the performance of all asset types across their portfolio. Today, I'd like to talk to you about one of our customers here in the Northeast, the city of Albany, and talk to you about the journey that they are going through across time to get to a more resilient, managed watershed for their citizens and for the businesses that operate there. One of the really cool things about what we do at Opti is we work on systems that have been around for a long time. And one of the happy side effects of that is we get a lot of really cool maps and drawings like this, and I'm excited to get to work some of those in today. Our story with Albany starts a long time ago. 1790 was the first year that the US Census was taken. And the important thing about this drawing, the schematic that was created by a survey in 1790, is that you can see that Albany is located on the Hudson River at the bottom there, and that it was built around a creek called Beaver Creek initially. Fast forward a few years, by 1866, you can start to see the shape of the city forming. You've got a grid-like pattern. And notice the contrast in color between the left side of the map that's fairly light still and the right side around where the city was building out. One of the key drivers for stormwater management need is urbanization, because when you start creating pavement, you start creating what are known as impervious surfaces, places where rather than before where the rain would hit the ground and soak in, now it hits the ground and runs into the local depressions, pooling, oftentimes causing flooding, getting people's basements, preventing roadways, basically causing havoc for society. And so stormwater management strategies will typically look to create places that water pools away from the places that cause problems and try to get those pools of water then out of the urban area into the natural waterways and creeks and rivers where it can be treated. Eventually, though, as urbanization continues, those creeks especially, but all the channels at some point, become a little bit too small, and you end up getting those basement backups, the flooding issues. And the first reaction that most communities had is make the creek bigger. In 1896, Albany did this by essentially taking Beaver Creek and burying it 50 feet below the ground in a huge sewer main. Now, we don't have to get into the complications of this, but you can see that this is probably a fairly disruptive process for a city, for anyone living around there, and that once you've built it, you've created a certain fixed amount of capacity to get the water out of your system. On the one hand, yes, big improvement, got a sewer main built, put the creek underground, paved over the parking lot, paved over paradise with a parking lot, et cetera. But fast forward another 50 years or so, and urbanization continues, urban growth continues, and you're starting to see little areas that were highlighted in this map that they produced as having regular flooding problems. So the problem still exists. Fast forward a few more years, and the goal changes a little bit, though. It's no longer just about flooding. Now society starts to care about the quality of the water that's actually discharged into that Hudson River. We joke in Boston a lot about the infamous dirty water of the Charles River, but 70 years ago, at the end of the industrial era in America, a lot of rivers were said to kind of ooze more than flow because there was so much industrial waste and sewage in them. And it's got so bad that in 1969, the Cuyahoga River, it's near Cincinnati, or near Cleveland, excuse me, actually caught on fire for the first time when a spark leapt from the railroad train next to it. That photo was actually taken at a similar event a few years before that, but Time magazine published it at that time, and it was part of a growing social movement that created a galvanized kind of grassroots interest in our country to not only establish the EPA, the U.S. Environmental Protection Agency, which is where regulation about the environmental protection comes from, but also create the Clean Water Act, which is really what creates the regulatory drivers that we operate under today. So the Clean Water Act is basically a regulatory framework for keeping water pollution out of our national waters. And it looks at the world, it creates a framework for doing so, and it looks at the world in two places. There's two kinds of polluters. There's point sources, basically a pipe into a place that can be easily measured. You can know how much pollution is happening, and you can trace it back up to somebody with a bank account. And so it's very easy to, in a regulatory framework, say, okay, there's so much pollution you can have, and we're going to make money available to deal with the reality as it is, but that's a very solvable problem. That's the reason why number 2 on the map over there, the wastewater treatment plants exist, because we said we can't be discharging raw sewage into the world all the time. The other thing, or the other sort of solution of pollution is non-point source, which is basically everything else. When you've got water hitting the ground, running across it, picking things up, dog pollution, excrement, brake dust, you ever get your brakes changed? Where did all those brakes go? It went into the waterways, just as tiny particles, and just got washed out there every once in a while. But basically, all of these are sources of pollution where it's really hard to know how much of it is happening, and it's really hard to trace it back to whoever did it. And so there's a different regulatory framework that was created, and it was really focused on what kind of conveyance system was in the city, whether it was a separate conveyance system for the rainwater and for the sewage, or whether they were a combined system, which mixes the rainwater and sewage at some point in the system, potentially causing other problems, which we're going to talk about here. Because Albany, to take it back, has a combined sewer system. So the Clean Water Act not only provided the definitions here, but it provides a regulatory framework for addressing these problems, which are known as long-term control plans. And under Albany's long-term control plan, they're committed to reducing the amount of that red overflow, that combination of sewage and runoff that enters the Hudson River over time. So how do they do that? So this is a better picture of a combined sewer system. Like I was saying, in dry weather, basically everything's fine. You get a certain amount of pollution coming out of the buildings, the toilets. It goes through a combined system, but eventually there's a path to a treatment plant caused by the first part of the Clean Water Act, which treats that sewage before it gets discharged into the natural waterway. But in wet weather, especially at big enough events, there is too much combined sewage to fit into the discharge to the treatment plant, and some of it ends up mixing with the river and getting discharged. That's the combined sewer overflow. The key thing is that it happens during wet weather. Another thing to think about when you're looking at combined sewer systems like Albany's, especially over time, and this is fast forward to near modern day, is that there are many different sources that contribute to that combined area. There's a choke point at the downstream part of the city, which is where a lot of the problems really start. And it's also the part of the city that's typically the oldest and the most expensive to build anything in, to do anything big, like building a big storage unit to keep all of that so it doesn't actually overflow. So traditional stormwater management strategies would say, we're going to solve this problem by creating storage all around the watershed in that upper reach so that the water doesn't necessarily get into the combined sewer as quickly. And it works. But there are some challenges and some trade-offs with it. For the purposes of our conversation, and I apologize to the water engineers in the room, we're going to call all kinds of stormwater infrastructure basically bathtubs with out-drain plugs. In other words, the rate of water leaving them depends on how much water is in them and how big that hole is. And you only get one chance to design that hole. You can make some trade-offs in that design. You can make it bigger so that the water moves away faster, which doesn't have nearly as much impact downstream, but makes sure that the local area has some place to drain around it. Or you can make it smaller, make sure that you are reducing the peak flows downstream, reducing that confluence, that choke point load, but at the same time, not getting as much benefit in terms of immediate flood reduction around the unit. And as the urbanization continues, these assumptions that you've built into the system become worse and worse. This is where Opti fits in. So Opti's products, which we deploy through a platform technology, enable an approach to stormwater management we call continuous monitoring and adaptive control, or CMAC. And our two ways of doing that are through product lines that enable control and monitoring of stormwater assets. They combine on-site conditions measured through sensors, flow control hardware like pumps and valves that we can install and commission or train partners to install and commission, and a cloud system that can keep keep tabs on everything that's happening, look at weather forecast, use control rules and rules engines to figure out how to actually execute on, moment by moment, moving the water to best achieve the objectives of those assets. And significant ROI is available when you are able to do this. Kind of the killer application of all of this is the ability to apply consistent behaviors and get the standardized performance metrics out of a wide variety of stormwater assets. This is one of those behaviors that's particularly relevant to combined sewer overflow. We call it smart detention. And what it does is very simple. Basically, before there's any weather coming, things are normal, things are just happening, everything's just normal. And then you see a forecast coming, and the system, if it decides there's a need for capacity to be created, and it has some capacity to create, is able to draw down, get rid of some of the water before the wet weather event happens so that there's more space to store it upstream. Wet weather happens, the system closes the valve, holds that discharge, unlike a passive system where the valve is always open and you're starting to get some of the rain that is just running into that infrastructure now discharged downstream. All of the upstream area can be kept back for the period of time, and there's rules to trade off how that works. And eventually, because it knows that it's not going to rain in the future, hold that water so that it's able to then allow the rest of the watershed to drain and then wait its turn to go through that downstream confluence point, avoiding the combined sewer overflow. And then, of course, after the storm, we can do things like attenuate how fast the water leaves, which can be helpful for other objectives like erosion control and things of that nature. Okay, so how does this apply to Albany? Albany had a long-term control plan that mandated an analysis of where the different sewer systems they were in charge of, how they performed, and where the opportunities would be. And in that, they kind of identified the Albany South aspect of their system as kind of the low-hanging fruit. Beaver Creek, where we mentioned earlier that Albany began, is part of this Albany South system. And what they basically were able to say is there's about 530 million gallons of combined sewer overflow from the Beaver Creek system. And we want to get that down to zero eventually, and we want to see continuous progress towards that goal over time. Otherwise, this consent order as a regulatory framework for enforcing long-term control plans. Otherwise, the next one might be a little more aggressive in terms of the money required to be spent. So all that was coming together, and Albany was putting their plans in place and started building traditional stormwater infrastructure. And then the baseline changed again. The goal changed around them. There was a flash flood event in August of 2014 where 3 inches of rainfall happened in an hour. This is a city that gets about 40 inches per year, typically. And that kind of reframed the thinking of the players that are involved here, because in the back of everyone's mind, there's this larger trend of every year we seem to have more days with larger amounts of storms, larger sizes of storms. I'm typically very skittish about showing any chart that's obviously that averaged, but I'm okay with it here because it's basically the same story everywhere across the country. And the symptom that was experienced was flash flooding around the Beaver Creek area, and then the larger context kind of created new energy for different approaches to managing their stormwater. And one of the choices that they made was they started working with Opti. And so this is where Opti then started working with the Albany Water District in order to take them on our journey to what we would call a more resilient managed sewer shed. All right, so here's a view of what that looks like. The first thing that they did was they got the Opti platform. This is the Opti Cloud solution. This gives them access to our customer success team, who is able to onboard them with materials about educating them about how these capabilities could fit into their system and help them understand how to actually go about procuring and installing these solutions. And the first thing that they thought about doing was a monitoring project, because new green infrastructure had just been put in. Green infrastructure is kind of like it's like a leaky bathtub of water infrastructure. The idea is rather than just catch it and then discharge it later, you catch it and you let it infiltrate over time, restoring groundwater, but also providing other benefits to the community. Everyone likes to live around plants. But it's hard to predict how effective it is because of the soil media and because of the plants involved. And so Albany said, well, we just put this in, let's monitor it and see how it works. And what was powerful about that is it actually worked better than they expected. Like I said, plants are hard to predict sometimes. You kind of have to see how it was built before you really know. And they figured out through the monitoring of this solution that there was more infiltration happening, and they were then able to route other areas that were adjacent to the original drainage basin into this piece of green infrastructure, saving on capital expenses and allowing them to prioritize other projects in their city. So that was kind of a nice quick win with data-driven decision-making and how they might be able to use Opti's products to manage their problem differently. It gave them confidence, and it made them start asking questions about how the control side of what Opti could do would apply to them. Now, simulation modeling is something that's pretty old in stormwater management. The schematic there on the upper left is from the software made by the EPA in the 60s. There's actually source code comments that say which punch card the lines are on still today. But what's great about it is it has a very standard way of representing how water moves around in a watershed, and a lot of people know how to use it. And it has an API that allows for control engines like ours to plug in and say, here's what the valves or the pumps are actually doing as the simulation plays out. And so what we did is we worked with Albany and their consulting partners in order to develop a simplified representation of their watershed that met enough kind of a back-of-the-envelope assessment of how this system would function, and made some assumptions about, there's 3 assets that they identified that would be interesting to start with. They knew that they were interesting because they were relatively new, so there wasn't much of a lift to figure out what they were and how to actually go about installing them. They knew that they were relatively large for the size of the watershed they were draining in, so even if this active control thing didn't work out, they could just turn it off and it would still add value for them. And they even got some grant money to help activate that sale. But the result of this simulation that ultimately was convincing here is if you look at it performing over a design year that was provided, so this is on the bottom there, you'll see that with about 20% of the watershed passing through Opti-managed storage, of the runoff passing through Opti-managed storage, they were able to get about 17% of a reduction on the thing that they're regulated for, the combined sewer overflow, the flow out of that combined sewer during wet weather. And so that was, even though the model was simple, compelling enough to get them interested in actually installing these Opti control locations. Now, there's 3 different locations online, and what I love about this is that they're all different types. There's a lake, which was built kind of in the center. You build a city on top of a creek, usually a lake happens, so that was the lake. There's a constructed wetland, and there's an underground detention basin. And the only thing that's compelling here to me is that they're all different, and yet they're using the same strategies with the same product applied to them. So they could be understood at a bigger level. And now the trust building process began. This is 2017, and when you go into the space that is currently using completely static solutions for their problem and you start introducing fully automated, sometimes I like to call it the self-driving pond kind of technology, there is a problem of getting the managers of the system to accept how it works and believe that it's what they want to do. And so one of the tools that we provide our customers in this process, for anyone who has a site installed on our platform, they get this thing called Event Explorer. How many of you are familiar with the concept of a social object? This is one of those ideas that was popular in like 2011 when everyone was trying to build the next Facebook of something. It's this idea that communities will organize around conversations that matter to them. So your job is the social object of LinkedIn, your life is the social object of Facebook, and for stormwater managers, storm events are the social object. Everyone likes to talk about the biggest storm that happened in their city and things like that. And so what Opti does is it provides an index, this Event Explorer, that lets our stormwater managers, the operators, and the analysts that are looking to design things in the future look at the history of their sites along an index of the storm events that happen. And what this does is it couples with our notifications solutions and our in-dashboard remote manual control to build a toolkit, a digital toolkit for trust building. Here's how it works. A storm is coming. Key stakeholders in the watershed will receive an email that has details like, hey, there's going to be a storm. These are the current status of all your systems. Here's how much rain we think is going to happen, and here's what we think we're going to do about it. If they don't like those answers or they're concerned about those answers, that person can click a link in that email, go straight to the dashboard, and start looking through Event Explorer at storms that were like the one that is about to happen in their past system. They then compare those behaviors, decide whether they thought it did a good enough job, and if they didn't like how it worked, set it into a manual override, take control themselves, and do what they think is better. This action, of course, is logged, so after the fact, whatever was done in the incident can be brought into a continuous learning and improvement process. But through that procedure, managers, and especially Albany, was able to start by letting the system, by driving it themselves, and eventually take their hands off the wheel and let the automation take place. So for the first 6 months or so of 2017 to the beginning of 2018, they were doing this trust-building exercise. But by March of 2018, things had largely stabilized. We'd made a few tweaks to the initial setup of the system, the configuration, and now it was in fully automatic mode, and it was starting to deliver considerable value. Each of these 3 sites, when compared to what would have happened if they were just operated in a passive mode, just open the whole time, was able to deliver, on average, a 6.5x improvement in that passive weather discharge performance. This is actual data monitored. This happened. It's still happening if it's raining right now. I actually don't think it's raining in Albany. But the point is, with a 6.5% improvement or capital investment increase, they're able to get a 6.5x improvement in the performance that matters. And this is an award-winning achievement that's been recognized throughout our industry for smart water management. So it's definitely also, in that sense, helping with the public perception that this water department is on it for their customers. Even though they had that 3-inch storm, things are changing. So again, this is the first 3 monitoring and sites were up there in 2011 or 7. Then we added a couple control sites. And then in 2019, they started thinking about, OK, let's take this to the next level. Let's start thinking about monitoring the actual impacts rather than having to show this passive model thing versus actual performance. Let's figure out how much impact these are actually making downstream. And so now we start working with, what's interesting about this is there's a wastewater treatment plant nearby, so there's already a stakeholder who's running a system like this, and now we're integrating with their capabilities and putting sensors in place that can monitor the actual impact of our controls, which will then inform the next generation of what we're going to do with this community. One of the, I think, incredible aspects of what that meant is they also decided, hey, we've got some new construction. This old stuff is working pretty well. The first 3 that we installed is working pretty well. Let's add Opti's control now to 3 more new construction sites, and let's not necessarily go through that whole rigmarole around doing that model ahead of time. And this is incredible to me because this is an agile mindset. This is happening within a water board. They're saying, we've got visibility into the impacts of our actions. We've got strategies and opportunities that look a lot like things that we've seen working. And we're going to be able to monitor the impact of them as soon as they go online anyways. So we're not going to necessarily prove exhaustively that this is going to work. We're going to take the next incremental step at adding capacity and measure that progress along the way. So this is the public sector, GovTech, doing agile development across a watershed because they have the right tools and the right support to make it happen. And I think that's incredible. And I think that's one of the things that we're working on at Opti is making that continuous improvement that you saw, I think it was Zach talking about a minute ago, happening in software, making that possible everywhere. And the long-term vision here is that downstream monitoring is actually going to fit into a larger control scheme that decides when water stays and when it leaves based on whether the actual regulatory objective is being hit or not, or will be hit or not. Obviously, it takes time for water to move down the stream, so there's some interesting forecasting that has to happen, but that's the algorithms, the analytics all of us are able to bring today. That stuff is becoming more commodity. And so this is not live now, but is being built, and I think it's going to be an incredibly exciting next case study to see what the performance improvement looks like when we get there. I'll take a step back. So I think a message that I hope has come out here is that getting IoT adoption in this real world context of water management or stormwater management involves a lot of building of trust. And something that I think happens when you put IoT products into a traditional industry is you realize, and this is probably true generally, but I haven't experienced it elsewhere because of my personal experience, is you can't control the whole process of that trust building. It happens organically, and you have to be okay with that fact because visibility is everywhere. The data is what it is. And on the one hand, that forces you to make decisions better or differently, that force quality to happen inside of your products because you know that you're not necessarily going to be able to choreograph the way that people perceive your actions. In this meeting that we were having with the Albany Water Department, one of the commissioners poked his head in the room and said, hey, how's that smart water system doing? And one of the engineers pulled up the dashboard that was in the other browser tab and looked at the last 24 hours of cellular connectivity, showed it to him, and he was like, oh, 99.9% online, this looks pretty good. And I'm sitting there like, we want to make this thing online all the time. Every single moment matters, but you never know how you're going to be judged and perceived. And being able to stand behind a product, thank you, Particle, for making the connectivity an emphasis, and because it's one of those things that continues to be an important aspect of building the trust necessary to get the water management in place and to solve these problems into the future. So looking forward, we're excited to be part of using IoT technologies to continue to advance the way that stormwater is managed across the US and maybe eventually elsewhere as well. We're starting to see some trends. Resilience is what we do, so we're always focused on making sure that our solutions are resilient so that they can make the watersheds that they're installed in more resilient. And something that we've seen lately coming across in the various smart cities conversations, I think there's a growing concern about malware, ransomware in particular. A lot of cities have been hit with that this year. And so we're starting to see very specific aspects or requests about what kind of technologies they want. Secure boot, for example, only running the firmware that your company deployed is kind of top of mind for a lot of cities at this point. And we're hopeful and optimistic that we'll be able to stay with the Particle platform. We've been with them for over 3.5 years now to continue to deliver these experiences and stay on the cutting edge of making cities more smart with the way that they manage stormwater. We're also excited about next generation wide area networks. We heard a little bit about that a minute ago. Subsurface monitoring, monitoring through hurricanes or other natural disasters. Those are actual salient use cases for our product line, and better networking technology will improve the way that our products can work. Not that they can't work well today. The smarts are on the edge, so we've got fail-safes, all of that is managed. But there's nothing like better connectivity to make everything go smoothly. And we're also invested in improving our quality of software development across the process and helping and, frankly, working with others in the Particle ecosystem to make sure that quality controls for the firmware are good. We've recently had efforts to use kind of traditional Linux sysadmin tools to understand exactly how much memory our devices are using at various points in their life cycle in order to make sure that connectivity and performance stays as high as necessary. And we have an open source project that all of you are welcome to look at that basically is a Raspberry Pi hosted test controller that can let you run any kind of integration test on actual Particle hardware we use extensively in our release process. Thank you for taking the time to listen to me. I am passionate about what we're doing because I think every day we are solving problems that are actually happening all the time. It wouldn't be possible without technology providers like Particle. We're a team of water engineers, technologists, scientists, business professionals. And we need to make sure that the IoT underneath everything that we do functions all the time, and Particle has made that possible over the last 4 years for us. So thank you.